Mark, why don't we dive a little bit deeper or expand on, in your framework and your set of principles, Macadamy's approach as it relates to data and diagnostics. We talked a little bit about this yesterday in the prep, but I think, bringing everyone a little bit more clarity around, what we mean. There's a lot of nuance here. And I've long said that particularly in the upstream, I don't care if it was when I was doing reservoir engineering work or trying to understand companies as an equity analyst, there's a lot of nuance that is unique to this asset class because of its inherent just natural randomness and variability. And when we talked earlier about gas composition, for example, hydrocarbons are not precisely manufactured. They are what they are.
Yeah. So let's just start with data, right? And I'll work from that. We have a range of people that we talk to. Some people say their data is good. Most people say their data is bad. I would say that even the people that say their data is good, that the first thing that we do on anybody is we approach it with physics. And the reason that we approach it with physics is because you don't need a lot of data to be able to understand, was the machine operating where you expected it to under those conditions, and did you see some sporadic things happening? And to the point of like compositional changes, especially with multi-stage machines, if you're seeing the same things happen across multiple stages at the same time, and physics allows you to do that, then you clearly know that this is something happening that's something like a compositional change that's happening that affects all of them together. And so it helps you start moving out those parts of the data sets and making sure that anything that you're doing with ML, you're training on just the data sets that are truly good data sets and not data sets that nobody knew about a problem during that time. So we trained in underlying issues or underlying differences, right? We have customers that came to us and said, hey, we'd like you to go through and look at this particular compressor. And it was in a hydrogen service. And so we start looking, we're like, with physics, you can see you're carrying over liquids. And so, that's the kind of thing they had no idea they were doing. So the very first thing is data. And the very first thing that we do anytime, and we're very pro on the ability to physics. So in this particular sheet, this is just our platform, and this is just showing connections of information. And we're not going to go through all these things. But what our platform is allowing us to do is have physics and machine learning all at the same level, all on the same platform, and the orchestration and the order that things are calculated can be based on the needs of that particular one. So these little lines help dictate orchestration and what happens first, which is really a critical part of doing this. You might want to do, and we have some use case examples in a little while where you might want to do machine learning with some data and then feed that into physics, or you might want to do physics and feed it into machine learning. And all of that eventually feeds into diagnostics. And again, the reason that we run physics first is physics is a fundamental. And then the other thing is most programs out there treat physics as, hey, am I running where I expect to be on my curve? And that's pretty much where they stop. But there's a lot more that you can do with it. So I think, in yesterday's conversation with you, we calculate what's the expected discharge temperature, what's the expected suction temperature, what's the expected discharge pressure. We calculate all these things, which give us individual deviations. And then within those, you take and you say, well, what's the power that my instruments are telling me I'm consuming from just, pressure, temperature in, pressure, temperature outflow? And where are you at on the curve, and what would the compressor or the pump say you're consuming? And then you compare it to the driver, whether it's a gas engine or a gas turbine or a motor, and which one's actually telling you the correct, which helps you understand, is this an instrument problem? So physics is powerful in being able to separate, is this an instrument drift problem? Is this a real machine problem? Is this a composition problem? So that's the very first thing, physics, right? And then the next thing that we do here is there are certain areas where we are real strong believers in machine learning. Machine learning, in our perspective in the machinery space, has been extremely powerful at figuring out the underlying physics on complicated things like one of the ones that we use it a lot on is vibration. You can go through, make sure that from a physics standpoint, you're running in normal operating conditions. You can then train a model on that data for the vibration conditions, or combustor, or exhaust cylinder temperatures. There's a lot of those complicated things that you can then train it on. And now you have something that's running that's giving you a deviation. And you'll when we get to like how we manage diagnostics and alerts, you'll see we pull these together based on what root cause we're actually trying to diagnose, at a level as you come down and you put all these different modes together. So physics and machine learning are, tied. They go together. One could go before the other. And I think that's actually very unique, and it takes care of that, data problem, bad data problem. We immediately, when you start running physics, you understand, hey, the customer said their suction pressure units were in PSI, but they're not. They're actually in inch ounces, right? It becomes obvious. All those kind of little things that when you talk about data, and normally the people that I think are telling you that you've got good data are data science people that can look at it and say, hey, it's got a normal variability, or we have tags that are mapped, right? They're not people that understand, does that number make any sense at all based on you just put 1,000 horsepower of energy into that fluid stream and it doesn't match anywhere close, right? There's a difference. So understanding data quality, the physics helps a lot with. I'll take a breath now and make sure that, this is all, and let you ask any questions before I do anything else here.